Welcome. Today's lesson is on the scientists Bronsted and Lowry and their definition for acids and bases. And this definition helps us to understand why ammonia, which has the chemical formula NH3, is a base. Now, if you remember, Arrhenius said that bases dissociate to form hydroxide ions and acids dissociate to form hydrogen ions. But there's no hydroxide in ammonia. There's no OH minus in NH3. So how is NH3 a base? Well, Bronsted and Lowry came up with a new definition that helps us understand this. And they said that bases actually accept protons and acids donate protons. Well, if we think about the acid definition, they're pretty much the same. Arrhenius, Bronsted, and Lowry all involve the hydrogen ion. But how does a chemical actually accept a proton, which is a hydrogen ion? How is that a base? Well, let's take a look at NH3. And let's take a look at what happens when ammonia reacts with water. And so here's the equation for ammonia reacting with water. And if you look at it, the products, how did we get these products? Well, ammonia actually accepts the proton or takes the hydrogen from water to form the ammonium ion, which is this. And what does it leave behind? It leaves behind the hydroxide ion. So now you can see with ammonia reacting with water, we also get the hydroxide ion, and that's why it's a base. So if one molecule accepts a proton, like the ammonia ion, then another molecule must be donating that proton. And here we have the Lewis dot reason why this happens, because ammonia has this extra lone pair of electrons that the hydrogen ion can attach to. So for Bronsted and Lowry bases, there always must be an acid partner, one that donates the proton for the base to accept. And the reverse reaction is true also. You have to have an acid and base on the other side of the reaction. So let's take a look at a reaction in a little bit more detail. Here's the same reaction of ammonia and water. If we look at ammonia from the left side to the right side, we can see the difference is this molecule has an extra hydrogen ion. So it must have accepted a hydrogen ion. And if we look at water to OH, the difference is it must have lost a hydrogen ion or donated the hydrogen ion. So that makes ammonia the base because it accepted the hydrogen. That makes water an acid. And yes, here water is acting as an acid. But let's also look at the reverse reaction, which is going on at the same time. Ammonia to ammonium ion to become ammonia again. What happens? It goes from NH4 plus back down to NH3, so it must be getting rid of a hydrogen ion. It must be donating a hydrogen ion. So it's an acid on this side. And the hydroxide ion, to go reverse to water, must have accepted a hydrogen ion. And so here, hydroxide, which we know is a base. So notice on both sides of the equation, we have a base and an acid, and the other side, we have an acid and a base. We call the right side of the equation conjugate, so partners. So this is the base, and ammonium is the conjugate acid, it's partner acid. And in reverse, water and hydroxide ions, water is the acid, and hydroxide ion is considered a conjugate or its partner base. So if something in one direction gains a hydrogen, the other reaction must be the reverse. It must lose a hydrogen ion. So if something loses a hydrogen ion one way, the reverse must mean it gains a hydrogen ion. And so that's why they're partners back and forth. Notice here we have a base acid partner, and forward and reverse we have a base acid partner. So let's look at one more reaction. And here we have the perchloric acid reacting with water to form the perchlorate ion. And this is a really important ion which we haven't talked about, but it's called the hydronium ion, right? So let's look at this. To go from HClO4 to ClO4 minus, what happened? Hopefully you can see it loses a hydrogen ion, so it must have donated, got rid of a hydrogen ion. And going the reverse direction, it has to gain a hydrogen ion or accept a hydrogen ion. And what's happening to the water? The water going from left to right must be gaining a hydrogen ion, and going from right to left, it must be losing a hydrogen ion. So, on this side of the equation, this is an acid. It is getting rid of or donating its hydrogen ion. And the reverse, it's accepting it. So on this side, it's an acid, and without the hydrogen ion, it's a base. What about the water? Remember, water was an acid in the last example. Here, water can also act as a base. To go from H2O to H3O+, which is the hydronium ion, it has to gain a hydrogen, and to go back the reverse way, it must lose a hydrogen ion. So these are acid-base pairs, and the products are conjugate bases and conjugate acids. So, how can I identify a material if I gave you a list? Is this a Bronsted-Lowry base or not? Well, you could pull out A10, and you notice a lot of the materials have to react with water to produce the hydroxide ion. It doesn't have a hydroxide ion. This one does not have a hydroxide ion. This one does not have a hydroxide ion. This one does not have a hydroxide ion. So you can use A10. All of these are Bronsted-Lowry bases. But you can also use Appendix A9. But you might say, but Miss Backus, Appendix A9 is for acids. Well, it's true, the forward reaction shows you the acid, but the reverse reaction will show you the bases. So if you look at this side of the equation, to go from here to here, it must have accepted a proton. So this is a Bronsted-Lowry base. So all of these molecules here are Bronsted-Lowry bases, because to go the reverse direction, they have to accept these protons to become these acids. So there you have it, a little bit about Bronsted-Lowry acids and bases. Thanks for listening.